them and then hope that the two that get thrown out are the bad grades.
I was talking to.
Well, I don't do two of them, and then I have to keep the bad grades.
You said there's going to be like what, 9, 10?
8 or 9. I'm not sure. I have 8 of them. I have 8 of them ready, and there's a 9th if I need it. All right, everyone. It's about time. Yeah, 1 o'clock. I was talking with one of your classmates that I'm in the doghouse. My wife is. I'm in the doghouse because she found out that I had an exam due today for a class, and she thought that was just cruel to do on Valentine's Day, you know. Well, yesterday was, right? So she's like, you have, you know, people having to work on this. And I was like, I gave them 2 weeks. So, all right, everybody turn in what they're going to turn in for the mini exam, if you're turning in. That seems brighter today for some reason. All right, you all ready?
Yep.
Okay, so please pay attention because apparently some of the things I say people don't hear. And so like, for example, the way I graded that last test, somebody got very upset with me because they didn't understand why -10 wasn't a 90. Okay, so please pay attention to the little details of what I say. I want to talk first about the mini exam I just passed out. Okay. Normally I just pass this out and say good luck. I'm going to talk a little bit about this one. So even though, well, you have everything you need to do this test right now. We've covered, there's nothing else that I need to show you for you to be able to do this. So you know what, before I talk about this one specifically, let me talk about just generally, if I haven't expressed this enough to you. The purpose of the mini exams for me is we're treating this is the what we call a capstone course. This is the end of the calculus sequence, right? You have Cal 1, Cal 2, Cal 3. Now, will you see calculus more? Yes, of course. But in terms of the calculus sequence, this is the end of it. So these mini exams are trying to like stir up all these things from Cal 1, from Cal 2, right? I've just got this big pot of calculus stuff that I keep on just stirring up, and these problems are requiring not only that you understand the concepts of this class, but yes, you may need to be able to do some limits and things like that. Go back, L'Hopital's rule. In this new exam, you're going to see that you're going to have to be able to demonstrate some techniques of integration, right? Integration by parts, trigonometric substitutions, things like that. So all these things are, the purpose of this is just so that it's fresher in your mind as you proceed through whatever other math courses you're going to go into, right? Because the further you remove yourself from doing limits and integrals, then that's just more you have to figure out later in another class, like kind of get it going again. So that's the method, that's my purpose, that's why I like these mini exams. They will start to taper off in terms of you needing to go back into the archives. As the mini exams progress, the problems will be just more suited, well, directly connected to the section where you're not having to just go back and, what was that weird algebra factoring technique I learned, right? Like you don't, that won't be as evident in the tests in the future. Does that make sense to you? Okay. With that said, let me talk a little bit about this one. So on number 1, there's only 4 problems on this test. So you can start it probably 10 minutes before it's due and you'll be fine, right?
Yeah.
Okay, find the value or values of t where the particle which moves along this curve, so I give you the vector function that draws the curve, right? And I give you a restriction on t, 0 to pi. And I ask, find what value of t that this thing has maximum speed, right? So that means you need to know, what the definition of speed is, right? Right here. Hold up. I don't have a stapler. Yeah, don't tear that off there. Yeah. Right across 8, 16, 3. Okay. All right. Okay. Part B. What is the maximum speed of the particle? Right? So find where it's reaching its maximum speed and then what is the maximum speed. So you have to understand what the maximum speed, how you can get that. I'm not going to tell you, but Okay, the second one, I give you an acceleration function, and I'm asking you to somehow go from that all the way back to the position function, and then once you find the position of that particle, figure out, what is it? Find a distance from that part. So you got this particle moving along some curve in three-dimensional space. All I'm giving you is the acceleration function. So you've got to figure out the position function. Once you do that, at t equals 1, your particle is going to be somewhere, and I want to know how far away it is from a plane. So that's, we've done that before. Yes?
Is that distance the shortest distance away?
Yes. Well, no, in this case, it's not the shortest distance because it's a point in a plane, right? So, well, you're saying, I think what you're asking me is, when you're talking about like a point plane, and we talk about the distance formula that we talked about in this class, it is the shortest, yes. So projecting like an orthogonal off the plane up to the point, yes. Okay, number 3. Boy, this one gets students. This one, they get real lost on what I'm asking for. Okay, I give you a vector function, right? Another vector function that draws a curve in space, right? And I tell you that if this particle starts at the point 0, 0, at the origin, and moves along this curve, and I tell you that it moves along that curve and it moves a total distance of 4 units, I want you to tell me where it is now. You have to just think about it. I mean, some people are just going to see it right away, but I'll let you mess with that, all right? The last one, I give you a vector function, but notice you have a constant in there, a. So a is unknown at that point. It says, this represents a helix. So we talked a little bit about this function. What it does is it draws kind of like a little, if a is fixed, it draws like the spring. And it says here to find the maximum or largest possible curvature and determine the value of A, not T, the value of A, which would yield that maximum curvature. So this is obviously going to involve curvature. You have to figure out what the curvature of this vector function is, and then you have to figure out where that curvature is the biggest it can ever be. And I will give you a huge hint that I normally don't give my students, and that is, if you ever want to find where any function gets to be its highest point or lowest point, you're back in Cal 1, right? You're back finding maximums or minimums. And if you go back and look at Cal 1, there were 2 ways we do that. You can find a maximum or a minimum if you're on a closed interval, or there's another method if you're on an open interval. So you're going to have to determine here if you're on a closed or open interval, but you have to show it to me algebraically with calculus. You can't just go to a computer and sketch the curvature function and say, oh, there's the max. You need to actually show it algebraically. Okay, that's all I'm going to say about it. If you have further questions, you can get with me during office hours. Anyone else need to turn in their mini exam? Anyone else turning in? No? No? Okay. All right. Yes?
Are we allowed to write on this piece of paper? It's not...
I don't want that back, yeah.
Good.
You're doing everything on separate, yeah.
Awesome. Cool.
All right, we are going to get into 11.2 today. This is a really interesting section. To me, it's a really interesting section, but this is not like a mission critical section, all right? If we don't get a complete grasp of this section, we're going to be okay moving along, but it just really brings up a very, very troubling idea when it comes to functions of 2 variables. So as a recap, last class what we did is we talked about this concept of, z is some function of 2 variables, and that draws a surface, right? Like generally speaking, this draws some surface like this, and we have as the domain on the ground, the domains on the ground, it kind of maps all these points, ordered pairs up into some z value. So that's what we have, right? So we're going to talk about limits of those functions. And to talk about limits, we're going to go back first to Cal 1, and we're going to remember in Cal 1 what a limit was, right? Back in Cal 1, we learned when you write limit x approaches a of the function, say f of x equals L, What that meant is that if you draw this function and you approach a from both directions, that your function is approaching some y value of L. So just show a picture here. This is the graph. This is the graph of the function f of x. This is f of x equals sine x over x. And so you can see from the picture that as I approach 0, right, when I approach 0, the limit is 1. So if I try and move in from both directions, right, both directions, those y values are approaching 1, aren't they? As I come into 0 from both sides. Now, if I actually get to 0, right, if I get to 0, it's undefined. The computer freaks out, doesn't know what to do, because it just tried to do 0 divided by 0, right? But the limit doesn't care about what's happening at 0, right? It cares about what happens as you get closer and closer to 0 from both sides, right? Do you remember in Cal 1, if we wanted to come in from one side, right? If we wanted to come in from one side, let me back this out so it doesn't freak out anymore. Okay, so if we want to come in from one side, then what we would do is we would put a plus here if we want to come in from the right, and if we want to come in from the left, we would put a minus here. And that would mean this would be the left-hand limit, the one with the plus would be the right-hand limit. So the good thing in Cal 1 was that if we wanted to know what happened as we approached some value, we only had to come in from two directions, right? Two places. Now, let's think about, let's see, here's another problem, just a picture. Look at what's happening here at 0. This limit would not exist, right? Back in Cal 1, if I asked you what's the limit of this function as you approach 0? Well, from the left you're headed to one place, right? And from the right you're headed somewhere else, right? They're headed to two different places there, right? So we would say here the limit doesn't exist, right? At 0. So everything's pretty straightforward in two-dimensional space. But when you get to three-dimensional space, we run into a major problem. So here's the notation. I'm going to write this on the side. If we write limit, and then we have the ordered pair xy approaches some ordered pair ab of that function f of xy, if we say that that equals L, then what we mean is that as we approach, as we take a point and approach this point AB, that the function's value is approaching L, right? That's what we're saying. Let me show this to you geometrically. Remember that I'm going to take this to the origin. Let's say we're looking at this function. Everyone see this as a surface, right? And that's some function f of xy. If I ask you right now to take the limit as your xy, that's your input, right? That's the thing that's going into the function. As that approaches the point 0, 0, which is the origin, right? I want to know what happens as you move towards the origin on this function. Right? If I ask you that question, what's the problem? Go ahead.
It's considered like every direction of the circle.
Yeah, how many ways can you approach that point from the plane?
Yeah.
Infinitely many ways, right? I mean, back in the previous problem when we approached x equals 0, right? X approaches 0, we could only come in from two directions, right? But if I'm trying to approach that point 0, 0, I can come in from, let's see, I could do this. I could come in along the x-axis and approach like that. That would be approaching 0, wouldn't it? 0, 0, sorry. Or I could come in on the other side, right? I could come in this way. That would be approaching 0, 0. Or I could come in down the y-axis like that. That would be approaching 0, 0. I could come in up from the y-axis. That would be approaching 0, 0. And I could come in diagonally, right, like that. I could even do some crazy shit, like I could spiral in, you know, like just spiral into the origin, right? Just that would be approaching 0, 0. I can pick any path towards 0, 0, and I have to check to make sure that the limit is giving me the same answer every time. So in Cal 1, we only check 2 directions. If they both matched, we're good. Here, we have to figure out a way to check every direction, every path leading to that point, which is impossible to do, right? That's impossible to do. We do not have a way of taking every single path there, right? We could take like straight lines, right? But that's not every way there. I could come in on a sine curve, right, and approach 0, 0. So that is a major problem when it comes to limits. So I say here, this means there are infinitely many ways that we can, ways or paths that we can approach the point A, B. All right? For the limit to exist at a point A, B, the limit must exist for must exist and be the same, right, for every single path we come in. So we come in this way, we get some limit, then we come in a different way, it needs to be the same limit, and every way, same limit. So we're going to take a look at our first example here. And we're going to see if we can investigate this limit, and we're going to try a couple of different paths. And I want you to notice that in all of the examples we do today, the problems I give you, we're going to be approaching 0, 0. That's only because we're trying to keep things kind of clean and simple. We could get different functions that are, we're approaching something other than 0, 0. But everything we do here today is going to be approaching 0, 0. So I'm going to write this down so it's a little bit bigger and move. So I have, I want to know what the limit is as the point xy approaches 0, 0. And here's the actual function. That is a function of 2 variables. And I want to know what happens, right? All right. So I need to pick a way visually. I'm trying to head to this point, and I need to pick a way, like a path to that point. So what do you say, just to kind of be consistent with what we learned in Cal 1, why don't we try and approach that point along the x-axis, like from both directions this way? Can we do that? Yeah? Okay, so if we do that, then what we're going to be doing is we're going to be imagining taking points here and sliding them towards that point 0, 0. If I pick a point here, so I'm going to say here, I'm going to approach along the x-axis. So if I'm approaching along the x-axis, then y would be 0, right? Because you're on the x-axis, not close to the x-axis. If you're on the x-axis, then y is exactly the value 0, isn't it? Yes? Yes? I'm looking at you. Yes? You sure? Okay. I want to make sure I get feedback here. If we're on the x-axis, right? All right, so this means that your y equals 0, right? And so what I'm going to do is I'm going to rewrite the limit right now, but I'm replacing y with 0. I'm not letting y get close to 0. I'm replacing y with 0. So let's rewrite this. Limit x, y. You know what? We're replacing y with 0, aren't we? So we're not letting x, y go to 0, 0. We're letting x, 0 go to 0, 0. And now I write x squared minus 0 squared over x squared plus 0 squared. See what I've done there? I want to know what happens as we approach that point, the origin, along the x-axis. So I fix my y to be 0. I rewrite the problem, replacing all y's with 0. And now some algebra happens, doesn't it? That fraction there turns into something a little bit nicer, doesn't it? I just get x squared over x squared, right? Which is just 1. So this limit as x, 0 approaches 0, 0 is just 1, right? I'm taking the limit of a constant now. And then that means my answer is 1. So does that mean the limit of this function is 1? No. Only along when I come in along the x-axis, it's 1. Right? Only then. So see if you can visualize this, and then I'm going to show you the picture. Imagine graphing that as a function, right? Whatever it looks like. What we're saying is that if you come in along the x-axis from both directions, whatever's happening to the function, as you get closer to the origin, the height of that surface should be getting closer to 1. Let's see it visually. Was this the... Yeah, okay. So let me get this stuff off the screen. So this is the graph of that function. I'm going to spin it around a little bit so you can see it. This is the graph of that surface. It's really a weird looking graph. It's almost like, did you ever like play that little game in school where you do that? It kind of looks like that a little bit, maybe not, but it's like folded, but it has this crease in it, like down here and up here. So what I want you to do is, everyone see the x-axis right here? Everyone see the x-axis? This green line, let's see. I'm going to come in here. How do I want to do it? Let me do it this way. So that green point is going to be moving along the x-axis, approaching the origin, right? And then this black point up here is the actual function's value at that green input. So when you plug in this green into the function, we're up here, aren't we? And if I move this across, plug it in, we're going to be up there. Notice that as I move along the x-axis, that the y value, the z value, that black point up there, notice it's always staying up there at 1. Even when I get to the other side. Now, it's harder to see it, so let me pull the opacity off the surface so you can see through it. Do you see that no matter which, if I come in from the other side of the x-axis, I'm always up there on the top edge of that surface. And that has a height of 1. Now, what happens when I actually get to the point 0, 0? This thing is undefined, right? Okay. So right now we know that along the x-axis we get 1. Let's check another path. Let's check along the y-axis now. So if I go along the y-axis, same function, right? Same surface. If I go along the y-axis, then x has to be 0, right? Because now what we're doing is we're looking at, this is the domain, right? The domain, I didn't write that on the last one. And our domain, we're coming along the y-axis, we're moving in this way now. We're approaching that point, so if we're along the y-axis, our x value is 0. All right, 3 times I've had to stop. What's going on, man? You got to be awake or something, keep the eyes open. All right, all right. All right, what am I going to replace here? If I'm going to come along the y-axis, what do I replace? You replace the x with 0. So I'm going to replace this with 0, and then I leave the y as y, still approaching the origin. And then up here with the function, I'm going to go 0 squared minus y squared over 0 squared plus y squared. Algebraically, again, that's all gone. So I have limit 0y approaches 0, 0. And then we get the same sort of algebra, except instead of getting positive 1 now, we're going to get what? Negative 1, right? Can somebody explain, raise your hand, why this is not undefined and why the answer is negative 1? I mean, I'm canceling the y's, right, or reducing them, and I'm just turning into negative 1. Why am I allowed to do that? This is a more like fundamental idea.
Is the function discontinuous on the x-axis?
Well, we know we can't plug 0, 0 into this, right? We know that the original function is totally undefined at 0, 0, right? You try and plug in 0, you get 0 on top, 0 on the bottom, right? If you plug in 0 for x and y. But here what I'm doing is I'm saying let x be 0, and then redo this, and then you're going to get this, and these cancel, I get negative 1. Why am I not saying here that this is still going to give me 0 over 0 and it's undefined? Did you have a response?
Well, any value other than 0 you plug in will have the same ratio on top and bottom.
It's a limit, right? This is a limit. We're not, when we evaluate a limit, what I'm doing here is I'm letting y, right? I'm letting the x be 0, right? X is 0. And I'm letting the y approach that y value of 0. So that means y is never going to be 0, right? But it's going to be really, really small. Well, it doesn't matter what y is. If you give me a really, really small number, square it, divide it by that same small number squared, that ratio will always be, well, in this case, -1, because there's a negative out here. So that's why I'm allowed to go straight from here to here and not say, oh, well, that's 0 is 0. It's not, because we're not letting y actually be 0. That's an important distinction to make, because it's a limit. Now, the x is 0. That's why I'm able to do this. It is 0 because I'm coming in along the y-axis. Let's look at it visually. Okay, so what you can see, this is that same graph. Notice along the y-axis, right? Coming along the y-axis, notice I'm down on the bottom. Let me bring that point in. See that point down there on the bottom? It's down below now, right? So as we come in along the y-axis for this surface, I'm down here at -1, which is what we said, right? At this point, what we can say is that the limit of this function does not exist. Because along one path we got 1, and along the other path we got -1. And that's the same in Cal 1 as coming in from both sides and getting two different answers, right? So let me kind of recap, and I'm going to say it several times here. With functions of two variables, in general, it's practically impossible, not always impossible, but practically impossible to figure out whether or not a limit exists at a point. It's easier to figure out if it doesn't exist. And the way we do that is we just check a couple of paths and hope that we get two different answers. If we get two different answers, then we know it doesn't exist, right? So that's what we're going to be focusing on. Can we pick paths and get the limit to be different from each path? That just summarizes it. Let's look at our next example. Yes?
So actually, I have a question. When you mentioned like having one variable equal to 0,
Yes.
does that mean like if you take a one variable limit on a multivariable function, it outputs a function of the, I guess, non-limited variable? Like how you set like y
Y equal to 0.
yeah.
We're coming along the x-axis.
But like if you didn't, and, like it didn't give you something that was undefined, would that output like a function of y? Like if you had like.
I think it might happen here, maybe. Maybe not. I'm not quite sure I understand your question yet, but let me keep going and then maybe. Is that okay?
Yeah, no, that's fine.
Okay. All right, take a look at this one right here. This is a new function, right? This is a new surface, brand new surface. I want to still approach the origin. We need to pick a path, right? So let's go with the same method we just did, right? You want to come in along the x-axis first? All right, so let's try x-axis first. I'm going to come in along the x-axis. To do that, I'm going to let y be 0, right? If I let y be 0, I'm going to rewrite the limit. I'm going to write x 0 because I'm letting the y value actually be 0. I'm approaching 0, 0. And now what I'm going to do is I'm going to I'm going to plug in 0 for x. 0 for y. So x times 0 over x squared plus 0 squared. That's the limit as the point x0 goes to 0, 0. I know it's a lot of writing. What is my numerator? 0, right? Because x times 0 is going to be 0. This is not a limit. That is the number 0. So the top is 0. And the bottom is what? X squared. So for the same reason as a second ago, this number up here is 0, right? And the number on the bottom is getting closer and closer to 0, but is it ever 0? No. So take the number 0 and divide it by any non-zero number, and what would you get? 0. So the answer to this is 0. So what I should expect is that I move in along the x-axis. I should be approaching 0, right, as a z coordinate. Only from that direction, right, from the x-axis. You want to try the y-axis, and then we'll look at the picture? What are we hoping happens on the next one? That we get what as a limit? Something what?
Different.
Different than 0. That's what we're hoping for, right? So let me try the y-axis. If I do y-axis, then x is 0. So I take the limit as xy, not xy, keep doing this. As what? 0y, thank you, approaches 0, 0. And now I'm going to rewrite that, but I'm going to replace the x with 0, so 0 times y over 0 squared plus y squared. And that is exactly the same principle as the previous limit, right? We get identically 0 on top, and on the bottom we get y squared, and that y is going to 0, but it's never actually going to be 0, right? So that should give me an answer of 0 as well. This is actually not good, because we're hoping for two different numbers, because now I've got to check a different path, right? And how many paths do we have? Infinitely many, yes.
Couldn't you like look at the equation and see the symmetry between them and see that no matter what number you plug in, you'll always get the same number? Or is there any examples where it would be different?
So are you saying that you're looking at this and you think that you can conclude from the symmetry that this limit should be 0 all the time? Is that what you're saying or no?
Well, the two, whatever.
Or from the two different paths? From these two different paths? Yeah, you could look at this and realize, hey, look, what just happened here is going to happen there too. But you're not saying like arbitrarily any path that's going to happen, right? You're not saying that. Yeah, so I agree with that statement. If you're just looking at these two paths, the symmetry tells you they're going to give you the same answer. But I need to try a different path now, right? And I get to choose from the bucket of infinitely many paths, right? So the path I'm going to choose is this one. And I'm choosing it because I've taught this class before, so I know what I want to choose, all right? I'm going to approach this point not along the x-axis, not along the y-axis. I'm going to approach it along the diagonal like this. I'm going to come into 0, 0 like this. And this line that I'm going to come in on is actually the line y equals x, isn't it? And so that means that what I'm going to do is I'm going to replace every y in this limit with x. That's what I'm going to do. So let me write this all down. I just wanted you to see visually what I'm about to do. So I'm about to now come down. My new path is going to be y equals x, right? This is the diagonal. I'm just choosing that because I know what's going to happen, all right? So if I do that, I'm going to rewrite the limit, and watch how I write this. I'm going to write xx approaches 0, 0, and then x times x over x squared plus x squared.